So this next chapter will be a pretty exciting one. It's extremely interesting. We're going to look at the entire history of our planet, all 4.5 billion years of it. We will use the rock record and specifically strata in the sedimentary rock to do that. We will also look at fossils to do that because both of these things paint the picture about how our planet has changed really dramatically over really extremely hard to wrap our minds around long amounts of time. So this introductory part will be all about the beginnings of this kind of thing and what the standard ideas and principles that geologists use to interpret the physical Earth around us. So we know that Earth is a dynamic and changing body, but virtually all of these changes do not happen on a human time scale, apart from volcanic eruptions sometimes do. Dating all the way back to ancient Greece, there were some people that recognized that because the landscapes around us, which clearly were formed or shaped by forces, it's pretty clear, or it's pretty obvious, I guess I should say, which rock formations are formed by water and which ones have been sculpted by wind, so on and so on. So because nobody notices these things change right before their eyes, it must have taken a really long time for them to have formed in the first place. So this is just a big treaty that Aristotle has. I'm not going to read it. But unfortunately, from recorded history until the 1800s, most scientists, and well, we didn't really have scientists back then, but most educated people and virtually all uneducated people, which was, most people back in these days, thought that the Earth was only a few thousand years old. And they would base the Bible off of that for the most part. The Bible didn't travel very far out of, Europe and the Middle East and North Africa until the time of Columbus. So what people in the Americas thought, what people in China thought, I guess I can't really comment. But anyways, our first sort of modern geologist was a guy named John Wesley Powell, and he was the first one to assume that Earth was at least millions of years old. It had to have been to shape these things around us. And what's useful for studying Earth's changing past is to look at sedimentary rock formations, because sedimentary rock formations reveal to us that that the environment around us for sure has to change. We've talked about this. The colors and things we see in sedimentary rock formations get there from the specific kinds of minerals that are there. Well, different minerals form under different conditions, some with lots of water, some with no water, some with oxygen present, others with no oxygen present. So these different layers tell us that that area has gone through transitions. And the kinds of transitions that sedimentary rocks record are these geologic events. Even today, geologists make use of these three main ideas. The first one is that the rock evidence shows both geologic events and changing life forms of the past. So the fossil record also tells us that there are all these creatures, both plants and animal, that did exist but do not exist today. The other main idea is that processes that occur on Earth today also occurred in the past. Now, that seems like kind of a no-duh statement, but it still does not really hit home with certain people today, and it did not hit home with people a few hundred years ago. What we mean by this is, let's take the rate of erosion. Let's say a rock formation erodes a couple centimeters a year, okay? Well, we look at that rock formation and you take notice of how many hundreds or thousands of feet or cubic meters or whatever have eroded from it. Well, you have to work backwards and figure out, okay, well, it would have taken at the very least, 100,000, a million years, whatever it happens to be. If you don't believe that the Earth is very old, if you think the Earth is only a few thousand years old, then this second thing doesn't work for you, because you have to assume that the entire Earth was created looking pretty close to the way it looks today. Or you have to assume that, for example, like a mountain range or the Himalayas or like the Grand Canyon formed in just a couple of days or a couple of weeks or months. And that just doesn't work. It doesn't conform to reality. And the last one is that Earth is very, very old and has changed over geologic time. We Used to have only one continent, Pangaea. Today we have several. Before that, it was, things were different. So Powell was inspired to do his work by actually visiting the Grand Canyon. He rafted down the Colorado River and he studied all the layers and he looked at it and he just imagined, because the Grand Canyon is up to a mile deep in some places, and he just thought, what was going on to have formed all these layers and colors and everything? Then in the late 1700s, a different person named James Hutton published a book where he proposed the fundamental principle of uniformitarianism. Uniformitarianism is basically what we mentioned earlier. All of the physical processes that go on today on our planet also operated in the past. So we see species evolve today because they evolved from their ancient ancestors in the past. It's the same story with, the plate tectonics. We can measure how fast they move today, and then we can work backwards and calculate when Pangaea formed, or was breaking up, And then that ends up matching exactly with how old the layers in the ocean, not the layers, but the crust in the ocean is, for example. So if we want to put this in simple terms, the landscapes and living things around us that do not appear to change very rapidly must have taken a long time to form in the first place. Influenced by Hutton, other geologists went out to interpret the rock record, and that's where we got all those principles that we mentioned earlier. So in their time, they could not analyze a rock or meteorite or anything like that and calculate its actual age. Towards the end of this chapter, we will discuss how that is done, but it's difficult technology. We needed to, it's radioactivity. We've only known how to do that for about the last, not even 100 years. So relative dating is just a method of placing rocks in chronological order. This will tell us which layers formed first, second, third, but not when they formed. But it's still incredibly useful. In relative dating, geologists use several important principles. So here we just have a layer of rocks, or of strata. The ones on the bottom are the oldest, the ones on top are most recent. Now, geologists figured this stuff out long before we could ever figure out exactly how old these layers are, right? Dinosaurs were being described and studied and put in chronological order in terms of when they appeared on our planet in the 1800s. It was clear back then that dinosaurs and humans, or we can pick another animal that's extinct. Let's pick like the woolly mammoth. Dinosaur bones and woolly mammoth bones are not found in the same formations, or at least not in the same layers, because the dinosaurs are found in layers below that of mammals, such as us or the woolly mammoths. So we already knew that these things occur in sequences, right? Now here, from bottom to top, it gets younger and younger. In this layer, it's been tilted sideways, so we have to read it from right to left, but we still can see a clear distinction between one layer with one type of mineral structure, so a certain environment going on, and then we move on to the next one where it's completely different. This shows that this area has been changing over time. We'll look at examples like these in class. So the first sort of assumption that we work through is the law of superposition. Sedimentary layers are deposited one at a time. So if the rock layer has not been altered like it has been in this picture, it's a little more difficult to tell there, but if the layers have been left alone, this reveals a really obvious pattern. The sedimentary rock layers, or you pick any layer, the layers below it are older than it, the layers above it are younger than it. Seems kind of like no duh, but we have to assume that that is indeed the way things work. If you believe that the Earth is only a few thousand years old, and so therefore dinosaurs were alive when people were alive, and were also around when woolly mammoths and whatever else kind of animals, then you don't believe that there's any such thing necessarily as younger layers and older layers. Maybe you kind of do, but you think that all the layers are so close to age together that they basically, you could say they formed at the same time, right? And that just isn't the way things work. So here's a bunch of layers, oldest one's on bottom, youngest one's on top. Now here's a heavily deformed sequence. So in a lot of places this gets disturbed, but this is the way things always happen in the first place. Wind and water are the things that move around and deposit sedimentary layers. Well, the wind and the water can't wash up layers in a pattern like this at the bottom of no lake or ocean anywhere in the world, and in no other place can you find layers that are deposited in a pattern like this. It's not possible. The laws of physics don't allow this kind of thing to happen, and it's very clear. All right, original horizontality picks on what I was just saying there. When layers are deposited, they do so on flat planes. There's no natural way for layers to form like this. Instead, movement and plate tectonics alters their position. So that's what we mean by original horizontality. All layers are put down flat in the first place. So in the Badlands in South Dakota, we don't really live next to any faults, right? The tectonic plates and everything are very far away from where we are. So the original horizontality is extremely well preserved here. So let's maximize this so I can use my mouse. If you look at these lines, just look at how perfectly straight they are, right? And then this line over here continues to over here, and then it keeps going all the way along this. That is original horizontality. Now, at one point, all of this, we can see that it's been eroded away by water, but originally all of this was like a flat plateau, like it is in the background, but way up here, right? All this stuff has just been washed away. So that layer would have continued through this empty space, but it's gradually eroded away, and that takes a very long time. So here's an example of, these are still layers. They don't intersect each other, they're parallel to each other, but they're curved and tilted, right? And they've been, over here in the back, we can see they've been lifted almost to a 90-degree angle. But that's from the Earth's crust changing and doing that to them. Originally, they were all flat. And the last one, which we call cross-cutting relationships, this now we're dealing with igneous rocks and other processes. If you can find a place where a fault line has shifted some layers relative to each other, that always happens after the layers have been deposited. So this will make a little bit more sense when we look at a picture here. So let's take this one. We can see all these different layers, right? We've got a gray layer, a pink layer, a tan layer, a dark yellow, light yellow, right? So this one formed first, then this one, then this one, then this one, then this one. Let's pick fault A because it's right here. Now notice how these layers are not continuous anymore. This fault shifted them, but it didn't shift all of them. See this one on top, it did not. So we know for a fact that layers, whatever this is, 1 through 2, 3, 4, 5, and then there's actually a sixth one over here. So layers 1, 2, 3, 4, 5, 6 formed before fault A formed. So we know that fault A is younger than it. And these layers on top, we'll call them 7, 8, 9, and 10. We know that those layers are younger than the fault, because if they weren't, well, they would have their position shifted as well, but they don't. Now dikes this is an igneous rock body. So if you can imagine a fault breaks right here, igneous rock can get in through that crack, and that's what's happened over here. So we know for a fact that all layers, 1 through 10, are younger than this dike right here, because it cuts through all the way. I'm sorry, I said younger, I should have said older. All of these layers are older than dike A because, well, it moves through all of them. They had to be there in the first place in order for that to happen. Geologists can relate rocks in one area to another, right? So this is something that Alfred Wegener was able to do. When he looked at fossils on different continents, when he found the exact same plants and animals on different continents, he knew that those continents were connected to each other. And because those continents were connected to each other, that would have to mean that the land, the terrain was identical. So when you find the fossil in South America and Africa, you know that the land was continuous. So we're not going to see a dramatic change from South America to Africa when they're connected right by each other. The environments were the same thing. So we can do that locally and across oceans as well with rocks that we find in areas. So if we want to do it locally, we can make a geologic column, which is just a model that arranges the rocks according to their relative ages, right? So this is a geologic column of the Grand Canyon. After analyzing and studying it, we know that the topmost layers in the Grand Canyon are really, really old, 250 million years old. That's about right when dinosaurs first started to appear on our planet. So it's really an incredibly long time. And then it goes down, and there are different types of rocks. If we start from the top, we see we have, limestone, and then if we go down further, we have sandstone, limestone again, much further down, and and there are some igneous rocks at the very, very bottom. In our neck of the woods, in the Badlands, we have these multiple different layers also. So we have the Sharps Formation, a rocky ford ash, that's literally volcanic ash deposited in one layer. The yellow mounds, which you can only see in one part of the park, that's a certain type of petrified soil. There's a word for that I can't remember off the top of my head, but yeah, there we go. So this is a geologic column. All right, inclusions. Sometimes a rock has other rocks, totally unique, different minerals embedded within it. So they come from when one certain rock gets weathered and broken down, and then it's covered by sediment and it's included in the new sedimentary rock that's formed. So the basic rule here is inclusions are always older than the rocks that they are found inside of, because they existed first, were broken down, and then put inside there. So this shows sort of the basics of how an inclusion could form. We have this igneous rock here. The surface gets weathered and eroded over a long period of time, so the surface has these small, irregular, broken pieces of that igneous rock. But then later the environment changes and a bunch of layers get dropped on, and we find the inclusions embedded within there. And here's a real picture of that type of thing. All right, so let's go back to this picture actually. What we can see is we have all these layers that are built up, right? Well, on the top we can see we have this layer, but there isn't very much of it left, right? Most of it's been eroded away. And as this gets left over time, maybe like the top 3 layers will just disappear from the rock record altogether. And we'll never see them again because they've just been washed away through erosion. So, that happens all the time. More often than not, layers get partially eroded and carried away. Now we can see when that kind of thing happens, and they're called unconformities. They indicate a long period where deposition of new sediments stopped. The layers that we had in place were eroded, and then later new layers get deposited on top of them. And there are different types. We have 3 of them, but they're all classified as unconformities. So here's this picture illustrates it a little better. We will start from the top because this goes back oldest and this is most recent. So we have layers, 1 through 6, and they're deposited because we have water. They deposit fairly quickly, and then that stops. So uplift happens, folding happens for whatever reason. The water drains away. So now these layers there's no new deposition going on. Well, the area is left alone for really long periods of time, and what happens? Well, the surface breaks down. So now we have layers 1 through 5 preserved kind of on the edge here, but in the middle, where that hump was, they're gone. And then later, things resume back the way they were before for whatever other reason. And so this is our unconformity right here, right? We have layers, in the middle we have layers 1, 2, 3, and then 7. Well, what happened to 4, 5, 6? Well, they're in place over here, but in other places, they're gone. Now, these are the 3 types, but we'll go into them here. So the first one is a disconformity. that forms between two different sedimentary layers, and they keep their original horizontality. The next one is an angular unconformity, which forms between different sedimentary layers also, but one of the layers is tilted relative to the other. The final one is called a nonconformity, and this one is unique in that it forms between igneous rock and sedimentary rock. And these are pretty easy to pick out because igneous rocks don't really form layers, and they stick out a little easier. So here's what an angular unconformity would look like deep below ground perhaps. So yeah, one group of these, if we look at these layers here, they're parallel to each other, right? Because we can see these perfectly straight lines, but they're not parallel in relation to these ones. So the unconformity is just the boundary where we have one layer and then all the different layers below it. And here are some just out in nature. So here we can see the tilted layers, all kind of tilted at the same angle. Then whatever was going on there stopped, and now new flat layers are being put on top. We can see the exact same thing over here. This one's really crazy. There's all kinds of tilting going on, but then we can see again flat layers on top, and again right there. Disconformities are really hard to point out in nature. The pictures that I have are not very good, but I mean, here we have flat layer after flat layer after flat layer. I have some things in class that I'll show you in person that are a little better. And lastly, a nonconformity. Again, this is igneous rock, so totally different in terms of appearance. And again, I don't have a good picture, but I do have something in class that I'll be able to show you. But just know that a nonconformity means there's igneous rock on one side and then sedimentary rock on the other side. Here's the Grand Canyon. So in the Grand Canyon, we have virtually most of the canyon, except the very, very bottom, has, even though it's incredibly deep, hundreds and hundreds, actually thousands of feet deep, the original horizontality is preserved all throughout. So there are a couple disconformities throughout there. Between these two groups, it's very irregular. So we know that this layer eroded away, and then on top of it, the red wall limestone was produced. Here we have an angular unconformity because these are tilted. And then there's some granite at the very bottom, so that's a nonconformity right there. Excuse me. Geologists use correlation to match rocks of similar age in different locations. So again, Alfred Wegener did this with his fossils, but we can also do this when he wasn't able to tell exactly how old those fossils were. When you do get the precise dates, then we can do this more precisely. If you find identical layers in different regions, it means those regions must have been under the exact same conditions at some point. For example, both of them were underwater, both were deserts, or with the same types of fossils. This is a little hard to model, but in Utah, we have, and I have pictures of both these places, Bryce Canyon and Zion Canyon. They're part of what's called the Great It's like Great Staircase Monument, because they literally form almost like a staircase, and the Grand Canyon's part of it as well. Basically, what we have here is when you're at the bottom of Bryce Canyon, you are walking around rock layers that are found at the top of Zion Canyon, right? So they're identical in mineralogy and age. So we know that, and they're not separated by very much distance. Today, because of plate tectonics, the area where Bryce Canyon is much higher in elevation than Zion. So the earth is basically tilted, kind of like this. But at one point, it was just this Navajo sandstone layer, right, on the very top.